Assalamu alaikum. From this lecture, we are going to start the second chapter of our textbook, which is Electronic Devices and Circuit Theory by Robert L. Boylston. The first topic of this chapter is load line analysis. Once the basic behavior of a device is understood, its function and response in an infinite variety of configuration can be examined. Until now, we have discussed the working and construction of semiconductor diode. Now is the time that we are going to discuss the function and response in different configuration. The analysis of electronic circuit can follow one or two paths using the actual characteristics or applying an approximate model for the device. So we can have the actual situation by using the actual diode characteristics or the Shockley's equation, and we can also apply the approximate model of the device so that we can have approximate solution, but we can get that solution in much easier way. So first one is to actual diode use actual diode characteristics or Shockley's equation using nonlinear mathematical techniques, and the second one is using graphical method by load line method. And approximate models are piecewise linear model, simplified model, and ideal diode model. For example, if you have this kind of circuit, which is maybe the most simplest one, where we have a resistor, a diode, and a voltage source. If you want to solve this circuit, uh, that means if you want to find the voltage across this resistor, voltage across the diode, and you want to find current through this series network, that means you want to solve the circuit, you can follow either the actual characteristics curve or Shockley's equation, or you can follow some simplified model or approximate model. The nonlinear mathematical techniques to solve these circuits uh, are like, if you have this circuit, you need to find current and voltages across these components. First, you can apply KVL in this loop, which is a single loop series circuit. By applying KVL, you will get this equation, that is E is equal to Vd plus Vr, that is rise of E is equal to drops of Vd plus Vr, and you know Vr is actually IDR, since ID is the current flowing through this whole series circuit. From this equation, you can find the relation of ID, which is equal to E minus Vd over R. And to find ID, you also have a Shockley's equation which defines the characteristic of this diode. Shockley's equation says ID is equal to Is e power Vd over nVt minus 1. Now we have two equations and two unknowns. Those two unknowns are Vd and Id. So you can find the solution with this set of equation, but solution of above equation require non-linear mathematical techniques. Now finding solution using piecewise linear method, Using KVL, again, if you apply KVL on this circuit, you will get this relation, that is E is equal to VD plus VR. And if you use piecewise linear model, that is you use RD instead of diode, that is internal resistance of diode is modeled here, and an ideal diode is modeled here. And for the voltage drop, we have mentioned this voltage drop on this resistor. So rewriting this equation will give us ID into RDC of diode plus ID into R. From this equation, we can find ID, that is equal to E divided by RDC plus R. Now we have only one unknown here, but you need to have the knowledge of Q point to find the value of RDC. Now another method is using simplified and ideal model. By simplified model, you need to replace diode with just a voltage drop of 0.7, provided the diode is silicon diode, and you ignore the resistance value. So applying KVL on this circuit will give you E is equal to VD plus VR, that is VD we already know, that is 0.7 volt, plus ID into R, that is the voltage drop across this resistor. And you can find the value of ID by rearranging this equation, that is ID is equal to E minus 0.7 over R. So you can easily find the value of current through this circuit, and of course you can find the voltage across this circuit, this resistor, by just putting the value of ID and knowing the value of this R. Now ideal model, we ignore both resistance and the voltage drop across the diode. So applying ideal model, if we apply KVL here, KVL will give us this equation E is equal to VR, that is IDR. Since there is we are considering there is no voltage drop on this ideal diode. In other words, we are actually ignoring the voltage drop and the internal resistance of diode. So ID will be simply E over R. Now using graphical method or load line analysis, let's assume you have this circuit, which is a series diode circuit, and you have a voltage source here with the magnitude of E, and we have a diode with this configuration, that is connected in this configuration, and a resistor R, that is load resistor. First you need to have the characteristic curve of the diode. That characteristic curve we can easily find from its datasheet. Now uh, how to actually find the operating point, or how to solve this circuit using load line analysis. First we need to obtain characteristic curve of the diode from its datasheet. Now we need to draw the load line. Now first we have to define what is load line. If you apply KVL on this series circuit, you will get this equation, that is E is equal to VD plus ID into R. Now this is the equation of a line, that is load line. We call it load line because the slope of this line will be determined by the value of this load resistor, that is R. Since we know that to find a line we need at least 2 points, so from this equation we first find 2 points, and later on when we will connect those 2 points we actually will draw the load line. First, the the first point which this line actually define is, with this equation actually define is, we find it on x-axis, that is on VD axis. And if you note that on VD axis we have ID equal to 0. So if you put ID is equal to 0 in this equation, you will get E is equal to VD. That is, VD will be on VD axis at the magnitude of E, which is known. You mark this point where VD is equal to E and ID is equal to 0. This equation is for actually ID equal to 0. ID equal to 0 milliampere. And about the other point, if you assume this vertical axis, that is y-axis, or ID axis, on this axis we have VD is equal to 0. So putting VD is equal to 0 in this equation will give you ID is equal to E by R. If you put VD equal to 0, then finding ID from this equation will give you ID is equal to E by R. That is, the value of ID is equal to the magnitude E by R. So let's assume we have E by R point here where VD is equal to 0 and ID is equal to E by R. So this point is at VD equal to 0, 0 volts. Now we have 2 points. If you join these 2 points, you will have this load line. The load line is defined by this network. Now to find the operating point of this circuit, we just see where this load line will intersect the characteristic curve of the device. The characteristic curve and the load line both intersect at this point, and we name this point as Q point or operating point. The Q point means quiescent point, that is not changing point. If you have the constant value of E and constant value of R, then this point is not changing. So that is why the name suggests that quiescent point or Q point. And that means this circuit is operating at this Q point. From this point, we can easily find the current which is flowing through the diode and voltage which is being dropped on diode. So uh, by drawing a line which is parallel to x-axis, or you draw the horizontal line from this Q point and where it cuts the y-axis, that will be the point IDQ. And when you draw a vertical line and where this line cuts the x-axis, that point will be PDQ. So in other words, you have find the value of IDQ and VDQ from this load line analysis. Now from example, we are going to discuss how to find the Q point or how to solve a series diode circuit using load line analysis. In example 2.1 of textbook, it says for series diode configuration of this figure, employing the diode characteristics of this figure, both characteristics and the curve, the circuit is given. Determine in part A VDQ and IDQ. That is VDQ and IDQ we need to find. This is Q point. And in part B we need to find the voltage drop at R. So for the part A, we first have to draw the load line. To draw the load line, we need to find 2 points which actually define that line. So since we know when we apply KVL on this circuit, the KVL give us this relation, that is E is equal to VD plus VR, that is ID into R. So to find 2 points, we find the first point, let's say on y-axis. On y-axis or ID axis, we know VD is equal to 0, and if you put VD is equal to 0, you will get ID is equal to E by R. So since E is known, R is known, you can easily find the value of ID, or the point uh, where uh, or the point on this y-axis or ID axis. So putting the values of E and R here, you will get the value, that is 20 milliampere. So you need to draw first point, that is 20 milliampere. And on x-axis, if you put ID is equal to 0 in this equation, you will find a point that will be equal to VD is equal to E at ID is equal to 0, and E is 10 volts. Since the scale of this x-axis is like this, that zero point 0.8 is here and 10 will be beyond this point. So if you consider 10, let's say here, then you draw the line which is load line, and where the load line intersect this characteristic curve of diode, that will be the Q point. So this means the 10 volt is around beyond the space of this slide, and if you draw or you connect these 2 points, you will get this load line, and where this load line intersect this characteristic curve of diode, that will be our Q point. This will be our Q point, and Q point means finding VDQ and IDQ. So drawing a horizontal line on parallel to this x-axis, you will find the value of IDQ, and drawing a vertical line, you will find the value of VDQ. So drawing this, you will get IDQ is equal to 18.5 milliampere and VDQ is equal to 0.78 volt. Now we have solved the circuit, that is we have found its operating point, or we have found the values of VDQ and IDQ. Now for part B, we need to find VR, that is voltage being dropped at this resistor R. So VR is equal to E minus VD, that is VR is equal to E minus VD. We can find this equation from the KVL equation. That means 10 minus VDQ, we should put VDQ instead of VD. 10 minus 0.78, that is equal to 9.22 volt. This shows out of this 10 volt, 0.78 volt will be dropped across this diode, and the remaining 9.22 volt will be dropped across this resistor. Now this is the same figure. Now the scale was mm, redrawn, and now you can see E there is one point, and at 20 milliampere E by R there is another point, and when you connect these 2 points, you are actually drawing the load line and finding the Q point where the intersection of load line and the characteristic curve is, and finding IDQ by drawing a horizontal line, and a vertical line will give you VDQ. Now another way is to find the resistance of diode from this Q point, and then finding the value of ID and VR. The resistance of diode, as you have seen when we discuss static or DC resistance, that is, you 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 can find resistance by this equation, which is V by ID, or VDQ by IDQ, that is 0.78 by 18.5 milliampere. This will give you the resistance of diode, that is 42.16 ohms. Now if you replace this value of resistance instead of diode, you can also find the value of ID and VR. So from this, if you want to find the value of ID will be equal to E by resistance of diode plus resistance of this load resistor. Or you find the current through a series circuit by dividing uh, the voltage applied to the total resistance of this series circuit. So you will get 18.5 milliampere, which is similar uh, as we have shown previously, and finding VR will give you RE over RD plus R. This is by voltage divider rule. You find the value of VR by simply multiplying R over RD plus R to the applied voltage, that is E. So this will give you 9.22 volts. So the results are similar to the previous slides. Either way you can solve the circuit. Now in this example we are asked to repeat example 2.1 using approximate equivalent model. Now as you know, for approximate or simplified equivalent model, the characteristic of diode is like this, where we 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 mention Vk, but we ignore the resistance. So you can see the slope is infinite. That is, you are ignoring the resistance, but you deploy Vk in this circuit. So we have this characteristic curve, and the load line is same, since this is defined by the circuit, the network actually. So 20 milliampere, and this point was 10 volts. So joining these 2 points will give you the load line, and the intersection of this load line to this simplified characteristic of diode will give you this value of IDQ and VDQ. So VDQ is now 0.7, as this is the line has no slope, so this should be, obviously VDQ will be equal to 0.7, but the value of current is almost same, that is 18.5 milliampere. So there is a little bit error in VDQ, but current value is almost constant or equal to the previous uh, solution. But one thing you must note, that drawing this characteristic curve is much easier as compared to drawing the actual characteristic curve. Drawing this, you have simply have to draw a line, straight line, vertical line from the Vk value, and below Vk you have current 0, that is on x-axis. From 0 to Vk the value of current is 0, and beyond Vk it rises sharply. So finding solution through a simplified equivalent model will give you this kind of solution, which have a little bit error but almost in acceptable range. Now in this example it says that we have to repeat example 2.1 by using ideal equivalent model. So it depends on the application that how much accuracy is needed. Then we want to choose the simpler and simpler model. Like in this case, if you choose ideal equivalent model have the characteristic curve like this, where we ignore Vk and we also ignore the resistance. So if this is Vd and this is Id axis, so ideal characteristic curve is like this. Now plotting the load line on this characteristic curve, the same load line which is defined by the network, that is one point is at Id equal to 20 milliampere and the other point is at Vd equal to E, that is 10 volt. Now you can see the load line intersects the ideal curve at this point, which is IDQ equal to 20 milliampere, and VDQ you can find uh, from this intersection, that is equal to 0 volt. Now the values are quite different than the example 2.1, but again it will depend on the accuracy needed for a particular solution. Previously VDQ was 0.78 on exact curve and IDQ was 18.5 milliampere. So of course the values are quite different, but again as I said, this will depend on the accuracy needed. And one thing you must note is that ideal curve is very simple to plot. Just along these axes we need to draw this ideal characteristic of ideal diode. So that is the end of this lecture, in which we have defined how to solve a diode network using load line. Thank you very much.